Good afternoon, everybody. I hope you're enjoying your lunch. Didn't realize I was going to follow Joe Gibbs, so tough act, but I'll do my best. So, as you heard, my name is Simon Gharibian. I work for Sikorsky Innovations. We're the advanced technology arm of Sikorsky Aircraft Corporation. So what I'm going to talk to you about today, since we're at the Internet of Things conference, is how Sikorsky Innovations is leveraging the sensors that we put on the aircraft and the data that comes out of those sensors to improve the safety, the economics, and the effectiveness of helicopters. Sikorsky has been around for over 90 years. Sikorsky Innovations is actually celebrating its 5th anniversary this year. So I've got a short little video to show you what Sikorsky Innovations has been up to for the last 5 years. If I can get it to work. There we go. All right, fun stuff. So let's start with the basics. By a show of hands, how many of you out there have actually been and flown in a helicopter? Oh, it's a pretty good crowd. All right. It's not too bad. And I'm going to assume, but you can raise your hands anywhere, how many of you have flown in a jetliner? I think pretty much everybody, right? You all use a jetliner to get here. So for the most part, although this crowd is pretty leaning to one side, helicopters aren't that mainstream. So, why are we so focused on helicopters? Why should you be interested in helicopters? Very simply, helicopters perform a mission that airplanes can't. By their unique ability to hover, they can do things that airplanes can't really do. As Igor Sikorsky, our founder, used to like to say, if a man is in need of rescue, an airplane can fly over and throw flowers at him. But a direct lift aircraft, like a helicopter, can actually fly in and rescue him. And we've done that over 2 million times since 1945. Helicopters also are runway independent, so they can land on things that don't need runways, like oil rigs. This has enabled energy independence and driven the economy. Just a fun note, 30,000 landings for a fleet of just about 200 S-92 aircraft works out to one landing every 9 minutes during the daylight hours. They are flying these aircraft 8 hours a day, 7 days a week. Since 1945, that was the picture I showed earlier with the R4, we've been supporting the warfighter for almost 70 years. Sikorsky Blackhawks, which is probably our most well-known product, have accumulated over 9 million flight hours and operated in every environment all over the globe, from deserts to jungles to urban landscapes. So you might be asking, why aren't you flying helicopters all the time if they're so great? Some of the problems with helicopters is that one of the problems with helicopters is they're slow. If I compare the cruise velocity of a real popular jet aircraft like a G550 to a common multi-engine helicopter, we're talking about almost a 4x difference in cruise. They're also very expensive. If I look at the dollars per flight hour for those two aircraft, you're looking at almost a 3x multiple. So those unique capabilities, the ability to hover, don't come free. And so while we don't think we're ever going to be able to hit parity with a fixed-wing aircraft, we definitely need to do things to close that gap. The other issue with helicopters is that they typically work in very risky environments. If you're plucking somebody out of a jungle, you're dropping people at offshore oil rigs, rescuing people from the top of a mountain, These are very high-risk endeavors, and as a result, helicopters get involved in a lot more accidents. If I compare a helicopter to, say, that 737 you flew in on the other day, we're looking at 11 times more likely to get into an accident. Now, Sikorsky aircraft, our popular S-92 commercial model, is vastly superior to this number. We're actually quite close to the airline number, but any number larger than 0 is completely unacceptable to us, and we need to do better. The other one is a side effect of vertical lift in that rotor system is vibration. Helicopters, simply put, vibrate everything. They vibrate the pilot, they vibrate the passengers, they vibrate the parts. All of that leads to expense. If you're a pilot in a typical Black Hawk, you get about 3 hours before you get tired out. If you're the poor guy in the back, after half an hour, you're done. You're tired. It's time to get off. So we've employed a number of things to reduce vibrations, but we're still not there yet. We can do more. So what is Sikorsky Innovations doing about these things? We're focusing on 3 areas, what we call technology pillars. The first of which is speed. You saw in the video the smaller aircraft that employs something we're calling X2 technology. It's the coaxial rotors with a pusher prop in the back. We've taken that technology and applied it to a larger aircraft called the S-97 Raider. First flight in May, pictured here. And we're looking at taking the regular speed of a helicopter and going about 70% faster. Now, that is while still maintaining the maneuverability and the hover characteristics that make helicopters useful. If you look at other types of vertical lift aircraft that can go fast, like a tilt wing or a tilt rotor aircraft, their downwash makes picking people up off, say, a rooftop in New Orleans after a hurricane a very risky endeavor indeed. It's not good to blow the people you're rescuing off of the roof before you can actually pick them up. Another area we're looking at, another pillar, is something we call autonomy. Now, I know there's the drone zone, and autonomy has been a pretty good buzzword. We define autonomy as a little bit different than what you might consider in the commercial marketplace. We look at autonomy as creating an operating system in the aircraft that allows us to insert a full spectrum of autonomous features. Now, that may be anywhere from the Sarah aircraft being able to fly completely by itself, hands off, no pilots in it, to the insertion of discrete autonomous features in a manned aircraft. Think of in your car where you have the button that allows you to parallel park. I'm not sure I would trust it, but it exists. Same thing for helicopters. We've inserted something called rig approach on the S-92. It automates the approach to offshore oil rigs. That was deployed in 2014 and has definitely decreased the pilot workload and allows the pilot to focus on other aspects of completing his mission, enhancing safety and enhancing effectiveness. But the final pillar is the one I happen to run, which is intelligence. Intelligence is taking advantage of the sensors that I was talking about and the data coming off of those sensors. And we are working really hard to create game-changing improvements in the areas of safety, the economics of the helicopter, and the effectiveness. So don't take my word for it. Let's look at some examples. So the first one I'll start with is safety. Pretty famous picture if you saw it on the news. That is an incident that occurred at Mount Hood in 2002. It's an HH-60G Pavehawk. It's an Air Force aircraft. They were going to pick up some folks who fell into a crevasse, and the winds changed, and they didn't have enough power to hover. And basically the helicopter sunk, rotor blades hit the mountain, and it rolled 8 times. Luckily for them, it was a Sikorsky. Everybody walked out. There were no major injuries. That aircraft was actually recovered and went back into service. But it was an avoidable incident. It all comes down to something we call power management, which is almost 20% of all crew-related accidents in helicopters. So there's things we can do better here. How do we communicate to the pilots? How do we communicate to the people operating these aircraft what the aircraft is capable of at any given moment? Basically, that involves being able to predict the performance of a helicopter, which is not as easy as you might think. It's based on a bunch of variables, some of which are environmental, so what altitude am I at? What's the outside temperature? What winds are there? And then other things are due to the settings on the aircraft. Am I running my air conditioning? Do I have my rotor ice protection system on? Do I have my engine de-ice system on that's bleed air? And then also payload. How much fuel have I got on board? How many of those hikers am I picking up at any given time? Right? So all of these variables factor in to the performance of the aircraft. Think about your car. You know, when you put a bunch of people and things in the back, it's going uphill. Going uphill is going to be a lot harder. It's the same thing with a helicopter. So the first step was to take the traditional way that we predict the performance of helicopters, which is with these very complex paper charts, and turn it into a calculator. And so we've done that. We've taken all those charts and turned them into an iPad application that basically the pilot puts in those ambient conditions, and it spits out the performance prediction for any given moment. So that's pretty good, but to be honest, it's not particularly gifted. It's a pretty straightforward solution. Where things get a little bit more interesting is if we connect that iPad to the aircraft. Now the aircraft, which already has sensors on it that know what the ambient conditions are. It knows what temperature it's at, knows what altitude it's at, knows the prevailing wind conditions. It can tell from stick position and engine torque how heavy it is at any given moment, where its CG is at any given moment. It starts telling the iPad all of that information, and live now we can tell the pilot what the aircraft capability is at any given moment. So imagine those guys on Fort Hood, if they had this application, they would be able to see that at that given altitude with the winds and the temperature that they were trying to operate in, they simply didn't have enough power to try and hover there, and they would have avoided that situation altogether. So that's step 2, but I think the ultimate is step 3, which comes into what we call our matrix technology, which was the autonomy part of our pillars. Eventually, you want to get to the point where you hit the go button, and the aircraft does everything itself. Right? The aircraft figures out how heavy it is, what the ambient conditions are, where you want to go, where you are now, and whether or not it's safe to proceed. And you simply operate the aircraft rather than pilot it. The next one we can talk about is economics. Operating a helicopter is relatively expensive. There's a lot of things that go into it. But the biggest piece of the pie is the maintenance, 39%. Some of the other costs in there are things like depreciation, insurance, cost of the pilots, cost of fuel. But maintenance is definitely the biggest portion of the pie. So what are we doing to help reduce the cost of the maintenance of the aircraft? And one of the things we look at heavily is the replacement of parts. And so I'm going to take a step back. Let's talk about things that we're all probably familiar with. So imagine you just purchased a shiny new Land Rover Discovery, and you're flipping through the owner's manual, and that owner's manual tells you you need to change the timing belt every 60,000 miles. I've been there. I think most of us have been there. So the manufacturers have basically said, hey, we're going to look at this timing belt, and we're going to come up with, we know from the timing belt construction what its acceptable damage limit is. We know when it's going to wear out, and we know when it's time to replace it. So we're going to make some assumptions since we don't know how you're going to drive your Land Rover Discovery. You might be the guy who goes off-roading with your Land Rover Discovery every day because it's capable of doing that. There it is in the deserts of Oman. So we're going to make this assumption that everybody drives this way, and we're going to tell everybody to replace their belts at basically the worst case. Because if you don't replace your belt on a Land Rover Discovery, you're talking about a $7,000 bill when the engine interferes with itself and damages a whole bunch of internal components. So we have to be safe, and as a result, we tell you the worst case, and we define 60,000 miles as a replacement interval. But in reality, a lot of us buy our Land Rover Discovery and we go to work with it, or we go to the grocery store, or it sits in the driveway. And so our actual usage and the damage that accumulates on that belt is a lot less severe than the guy driving it in the desert dunes of Oman every day, right? And so the difference between those two, it translates to money, right? In this example, which is completely notional, I'm sorry, Land Rover, I made it all up, but at the end of the day, in this scenario, you're talking about replacing your belt 3 times as often as you might actually need to if you knew the accumulation of wear based on your driving style. And so that difference is the money that we're looking to save here. So how do we figure that out? How do we know how you're driving your car, or in our case, how do we know how you're flying your aircraft? So the good thing is that most modern aircrafts, including ours, already collect tons of data. Sikorsky was at the forefront in 2004 when we deployed the S-92, the commercial helicopter, with something we call health and usage monitoring system. So we've actually been collecting data for over 10 years now. And that information is coming off the helicopter, tells us about how it's being flown, so general stick positions, speeds, altitudes, what we call state data, just the basic stuff. Plus, we put sensors on the critical driveline components because those are the things that drive maintenance costs. So we've been collecting that data and doing a number of things with it that I'll explain in a second. But what's getting interesting is that as helicopters get more advanced, like this Canadian CH-148 that has fly-by-wire, there's a bunch of other sensors that are used particularly just to control the helicopter with a fly-by-wire system. So if we can take those sensors that are already on the aircraft and combine them with that basic generic state data, we actually can start predicting the loads on components that don't have any sensors at all. So rather than go in and place sensors on every component of the helicopter that we're interested in, we can combine the information that's coming off existing sensors and do more interesting things with them and basically derive a bunch of conclusions of the loads on those components. But of course, we have to be accurate. We can't underpredict the load on a particular component because that could mean that we would prescribe its replacement after it perhaps has too much damage on it to be safe. So what do? So we go off, we instrument the heck out of an aircraft, and we fly it. And we come up with test data. Hope you guys can see that. Yeah. So we'll fly around, all the different conditions, we'll get all the test data. Then we can compare it to the predicted loads that we're getting from the combination of that state data and a couple strategically placed sensors. In this case, the correlation is close enough that we can actually use those predicted loads to then prescribe the maintenance interval for that particular component. That's intelligence. By doing this, we're seeing that we can reduce the cost of those parts over the life of the aircraft anywhere from 20 to 40%, because you're basically taking advantage of the difference between removing and replacing a component at the composite worst case versus actual usage. We've been doing this. 250 aircraft worldwide, over 10 years of service, almost 1 million flight hours, 16 terabytes of data. We're using this data today to grant life extensions on the aircraft. So if you're flying around and you've basically been operating straight and level, back and forth to an oil rig, no extreme maneuvers, we can say, okay, you can keep that particular component on wing longer than, say, our other customer who's flying nap of the earth and inserting people in covert operations. The other big thing that we're doing with the data, and we continue to want to expand, is what I call downtime avoidance. So imagine you get up in the morning, you've got a big day, you got a, say, job interview or a big meeting at work, you hop in your car and you turn the key, and nothing happens. Now you've got a crisis, right? You got to deal with a dead car, you might have to jump start it, you might have to get people out to help you. That, in the aircraft world, is considered an aircraft on ground, AOG event. We have traditionally gone to extraordinary lengths to solve AOGs for our customers. Sikorsky has a policy for our commercial customers of 24-hour response time. We've been known to charter 767 aircraft to get parts from Connecticut to Norway to get an aircraft back in the air. That's a very expensive way to run a business. So the more we can do to turn those unscheduled events into scheduled events, the more money we save our customers, the more money we save ourselves. All right? So it's turning that event where you get in the car and you turn the key and nothing happens. Imagine your car said a week earlier, hey, you know what? My alternator seems to be making a funny noise. It's vibrating differently. The voltage coming out of it is starting to drop. We think you got about a week. You need to change it. Right? Now you can start shopping online. You can get a cheaper alternator from Amazon. One of those drones comes and delivers it for you. Right? You can schedule it over the weekend. You can replace it yourself. Right? It becomes a non-event. Maybe a hassle, but a non-event. You're not missing your meeting. You're not missing your interview. That's downtime avoidance. It also helps you optimize your maintenance. Maybe while you're in there replacing the alternator, you're going to change your spark plugs because you might as well, and you're doing it that weekend, and you got all your tools out anyway. So that helps us there as well. We're definitely moving from what happened, using the data to figure out why something went wrong, into using the data to predict when something will go wrong in advance so that we can pre-position parts and labor and make sure that that helicopter is always flying. So the last thing I'll touch upon is what I call effectiveness. Like I spoke earlier, vibrations really degrades the effectiveness of the aircraft and the crew. And no matter where you are, a helicopter has a job to do. It's got a mission that it has to perform. And so the more effective we can make the aircraft, the more basically bang for the buck the operator gets from owning that aircraft. So one of the ways we combat vibrations today is with a combination of active and passive systems. We've gotten smarter over the years, but at the end of the day, we're combating vibrations with counterweights. So imagine that for a second, right? If you've seen aircraft, you've seen helicopters, we go to extraordinary lengths to reduce the weight of a helicopter. We'll spend thousands of dollars per pound in weight improvement ideas to get weight off of the helicopter. Then we'll go and stick 250 pounds worth of tungsten on the rotor head to combat the vibrations coming out of that rotor system. And not doing that good a job. Right? Think about that. Besides that, that device is called a bifilar. It's got a bunch of moving parts. That guy has got to stand up on that rotor head in 120-degree desert weather to clean the dust out of it. Otherwise, it doesn't work very well. So there's got to be a better way. So one of the better ways that we're combating vibrations is with an active system called the hub-mounted vibration absorber. This is basically like a spinning weight. So if you've ever taken a weight on a string and spun it around your head, you're creating a force. The key here is the sensors that are in the aircraft. The sensors in the aircraft are able to measure the vibrations, and as a result, we're able to time the spinning of that mass to counteract the vibrations coming out of the rotor system. It's a bit like the noise-canceling headphones, except done with physics. So by spinning this mass in the rotor system, I can combat the vibrations extremely effectively. Let's see if I can get it. So the question is, how well does it work? So if I plot the vibrations in different locations on the aircraft and draw a line that's basically your jetliner smoothness, your current Black Hawk that's in the U.S. Army inventory doesn't do that well. And that's with active systems, state-of-the-art. With our zero vibe system, the hub-mounted absorber, plus a couple absorbers that are on the transmission, we can get this to jet smoothness. The point here is that you're not only smoothing out the ride for the pilots and the passengers, making their mission effectiveness better, right? They can operate longer, they can fly longer, they don't get tired out. You're actually wearing out parts less. We found that reduction in vibration level has a direct correlation to reduction in part failures and part removals. To top it all off, I can actually cut the weight of the vibration suppression system in half by using these active techniques. But it all comes back down to sensors. So that is kind of the crux of the reason I'm here at the Internet of Things conference. We need sensors. The sensors on our aircraft are good. They've enabled the things that I've shown you. However, they tend to be hardwired in. And once you're hardwired in an aircraft configuration, it becomes a very difficult thing to change it. So we're really looking for state-of-the-art wireless sensors, preferably ones that are power scavenging, right, so that they harvest their own energy, can transmit their data wirelessly, so I can put them in different places on the aircraft. I can reconfigure them as I need to. But they've got to be rugged. You can see our helicopters operate in some of the toughest places in the world, right? From deserts to off of aircraft carriers to, well, we're putting a couple in the Arctic Circle right now. So those sensors have to be able to operate reliably. I don't want to have to deal with them. I don't want to remove them. I want them on the aircraft accurately giving off data for over 10 years. And that's where you guys come in. Sikorsky has got a thing called the E-Challenge, Entrepreneurial Challenge. We have a $25,000 cash prize that we're offering. We're looking for partners. You keep the IP. We want to just work with you. We want your stuff on our aircraft. We want the latest technology. We believe that there are tangential industries, especially in this world, that focus on things like sensors that we can use in the helicopter world. We need you to come forward. We need you to let us know what you've got so that we can see if it works on our helicopter and we can partner for the next generation. So I've spent a little bit of time. I hope you found this interesting. We've shared a couple things, a couple examples of how Sikorsky Innovation is working hard to change the game for safety, economics, and effectiveness. It's no longer about adding metal to an aircraft or more power or spending more money. It's about coming up with an elegant solution, and we believe intelligence is part of that. Thanks. Thank you very much. I'll take questions at this point.